So let's talk about Matlab. Now, for those who don't really know Matlab is an interactive environment where you can model and code stuff that will be used for prototyping or for algorithm development or for theoretical discussions. The reason why I'm telling you this is that Matlab is not really a final product deployment environment, because your aim is not to deploy something and mass produce it or anything like that. It is more about trying, failing, and then readjusting and simulating stuff. Therefore, it has a interpreted language. Therefore, I don't really have to compile anything like C. I can just code it. I can just say A should be equal to 2. Now A is equal to 2. So it's kind of flexible and fast and easy to use. Therefore, you can just use a little bit MATLAB, and after some time, you will be used to it and it will just flow right away. Of course, I'm talking about the basic MATLAB interface and the MATLAB programming language itself. So, yeah, I'm going to just briefly touch base on the basics, because you can go ahead and examine the PDF on for more details, first of all. And second of all, I don't want to bore you too much with some stuff. You have maybe used MATLAB, so I'm going to speed up. But if you have any questions, feel free to ask at any point, so we can clarify that that we are not missing anything. So, yeah, how do we define variables? Because variables are essential. Well, we give it a name, we use the equal sign, and then we assign it to a value. Now, it is important that we assign it a value, because it's not possible to define a variable by just giving it a name, because since it doesn't have any type, in MATLAB, we don't use data types, not in the sense of C. Therefore, it needs to use the right-hand side of the equal sign to assess what the type is. So therefore, for example, if we assign x to 123.3, it is obvious that we have a floating point number on the right-hand side, and it'll be a float type variable. Now, in case of MATLAB, of course, since we want to be flexible, and since we think that since we assume that we are doing scientific stuff, we need more precision. Therefore, the basic data type in MATLAB is not float, it is double. So we have double precision, high precision calculations. Therefore, this data here is actually a double type of data. Now, if we use just one single quote to define a character, if you are using C, you would be familiar with this single quote and single character type of thing. But in MATLAB, this is extended so that you don't really have to use just one single character. You can just use multiple of them. This is important to know, because if you would have used, for example, C, it would look like this: char C, for example, and then there's a certain buffer to it, and then you would just give it something like this, maybe something like this. So it takes even quite some time to do this, but you get the idea. Here, you don't really have to provide the length of the string, since it can be counted from the right-hand side, and it is an interpreted language, so they got rid of that. It is quite flexible. You can even extend it a little bit more, and it doesn't really matter. So, but of course, since we have no type declarations, since we are sticking with the flexible side of MATLAB, it might be an issue in terms of performance, because we are giving up performance a little bit for flexibility. But that's okay, because we are not going to deploy MATLAB. We will, for example, in our course, we want to try some control systems. We want to design some control systems. We want to come up with a controller. once we have done that, we can just go ahead and use optimized structures and optimized piece of code to deploy. But here we have to first come up with the theoretical design or with the design itself. So therefore, we are giving up speed, but it's not really that relevant in our case because, well, yeah, we want to simulate design, come up with designs. So performance is not really that important. Now, it is also important to note that the Boolean type is not really called Boolean, it's called logical. So it's kind of this, if you had the logic lectures, you know what I mean by logical 1 and logical 0. It's just a bit that can be a 1 or a 0. It is calling back to the logic design course. So it's not called Boolean. And you can also use true, false, as you can see. Or if you're really fancy, you can just use logical and then provide it the value that you want, and it converts it to a logical 1, 0. By the way, we can use just single quotes to define variables, but it is also possible to do this with double quotes. Now, it would seem like that has no meaning here, but it has. And the basic difference here is the following. If you know some other programming languages, like maybe C# or Java, also C++, they have a string data type, which is called string most of the time. And that string has actually capabilities to it. It is an object type. Therefore, if you use double quotes, it would mean that you are dealing with string manipulation, text manipulation, etc., because this has the capabilities for it. If you are using the single quotes, it means that it's just a text, nothing more. You don't want to, for example, search for A's and replace them with something else. You don't want to split the string into its delimiters with commas, etc. You don't really want to do that with a single quotation string. You would rather prefer double quote strings. And if you add up, for example, two string data types, you would end up in a concatenated string. But if you would repeat that for single quote, you can see that, first of all, it says that it is a matrix, and you cannot really add them together. So you can see that they are basically quite different as data types. And the reason here is that single quotes are basically coming from the fact that we are using ASCII tables. And rather than having ASDA, we can convert it into, for example, integers. And we can see that actually we have 97, 115, 100, and 97 again, which means that A on the ASCII table is basically 97 as a decimal number. And by defining them with single quotes, the only thing that happens is that we are defining numbers, and it is in fact a row vector and nothing else. And if the size does not match the length of the strings here, or character arrays, if they don't match, you cannot add them because it treats them like numbers. So therefore, if you want to manipulate the string, please use the double quotation. If you don't want to use it, if you just want to define a temporary string, then you can go ahead and use the single quote one. Yeah, how do we define arrays? We define arrays by using square brackets. And it is kind of the C approach here, where you use this, for example. But since we are not we are not defining types here, we just use the square brackets. And since we want to provide the values and the length of them will be calculated based on the value, we are just dropping this whole thing here. And also the type, we just equate it to the array or the vector here. Use square brackets. You can use a comma as a separator, or you can just use space. It's basically the same, but when you copy and paste code, it is better to have commas because space can be can cause problems because accidentally you might get rid of the space. And since it's just a space, you might not notice it, but then you have just manipulated the data and it's not correct now. But using commas is important. I'll try to use commas all the time. Now, Matlab, the name of Matlab comes from Matrix Laboratory. So basically, the data type that Matlab relies on is actually matrices. So even though if I'm defining a equals 2 as a scalar, it's still a 1-by-1 matrix. Therefore, if I'm defining a vector like this, this is actually a row matrix. Now, it is also possible, therefore, to define it like a column vector or column matrix. And you can do that by using the transpose operator, which is just shift-2, or this apostrophe here, and it'll display it as a column. Now, this is one way of defining a column vector or matrix, and the other way would be using semicolons. Of course, in the editor itself, not here, you can just use enter and put them on top of each other like a column and define them, but I like to stick with semicolons. So this is the way we define basically a column vector. Now what we can do is we can do the following. Let's have a row vector of 1, 2, 3. Let's have another vector 3, 4, 5. And let's say I want to stack them on top of each other. So what would I do? Let's say X is our new data type. And basically, I want to define the first row from A and then the next row from B. So this would stack them on top of each other. This means that A should be the first row and B should be the second row. And if I do it like this, you get a matrix. So, and if you look closely, what this means is it is actually nothing else but this. So we actually use commas to indicate what should be next to each other and semicolons what should be on top of each other. So, and you can also get rid of the unnecessary extra brackets here because it's kind of crowded here. You can just open a bracket, define 1, and then next to it should be a 2, next to it should be a 3, new line, 3, next to it should be 4, and 5. And that's it, that's my array. This is kind of a 2D array, and we are creating it row-wise. So this is a way of defining matrices. Now I'm curious, and I do this all the time, I'm curious about the fact that couldn't it be possible to define it column-wise? Because all that I'm doing here is I'm defining the rows and I'm stacking them together. What about the columns? I can do the following. I can just take the first column, 1, 3, take the next column, 2, 4, the next column, 3, 5. The only thing that is left is to stack them together. Let's say our matrix should be A, next to it should be B, next to it should be C. There we go. It's still the same matrix. And this time I did something else. I stacked them column-wise. So basically, this was 2, 4, and then this was 3, 5. So you can create this as a matrix. And what happens if you get rid of the extra brackets here? Do you think it will be possible, it will run without any error, or will we see a problem? Will this work? Sizce çalışır mı? Yoksa hata mı verir? What do you think? Anyone? Well, let's try it out. if I hit enter, I see that the dimensions of arrays being concatenated are not consistent. It gives me a word-cat error. So what this means is that if you look closely, actually, it doesn't really make sense. Why? Because first row should be 1. The next, we go one line, we start a new line, and 3 and 2 should be side by side. And then next line is 4, 3, and then next line is 5. So we have a 1-element row, 2-element rows, again, and then again 1-element row. So it's not really a square shape. So therefore, it's not possible to do it with this shortcut. You have to use double brackets here in this case, because they are not size compatible. If you remove these brackets here, it changes its meaning, because comma is a side-by-side operator where semicolon is on top of each other. So therefore, it's not the same. But here you can feel free to use it like this. If you are using a row-wise definition, you can just go ahead and use it like this with double brackets or just single brackets. It works, but this is not the same. So yeah, we can define matrices using some predefined functions. For example, zeros. You just give it a shape, rows and columns, and it will create you the matrix that consists of only zeros. And by the way, I used help zeros. So there are 2 ways of getting help with Matlab. One of them is help. You can just use help and then space and then the name of the function that you want to use. But if you're using help, don't expect much explanation, because it is to remind you of zeros, for example, in this case. But if you are new to this function and you don't know really what how to use it or what it's really doing, then you should use doc zeros, which stands for documentation. If you enter this, you'll see that a pop-up occurs, and hopefully, there we go. And you have the documentation page, which is more detailed. It explains everything. It has neat examples, and you can just use this as a reference material. And let me show you something else. If you open up a browser and type in help zeros Matlab, you'll come to this page, which is exactly the same page actually. So it's basically the same page here. The nice thing about the documentation embedded into Matlab is, as far as I remember, that it doesn't require any internet connection. So if you're not connected to the internet, if you're on Matlab and you want to look up a documentation, you can just use the built-in documentation because it doesn't need any internet connection. So now help and doc can be helpful. Sometimes I type in something like CLC, which means clear console. So it gets rid of this clutter here. CLC just clears the terminal. And there's also something called clear, which gets rid of the variables that were defined. So a is equal to 2, CLC, and a still lives here. If you're using the Matlab GUI, you will see that there's a workspace. And in that workspace, you will see all the variables that are present. But if you call clear and then look for a, you can see that the memory is wiped out. You don't have any definition from the previous codes before clear. So there's nothing left there. Clear gets rid of all the definition that are there. So you wipe out the memory, start fresh. So let's start fresh. Let's clear the console. Now we have kind of reset the whole Matlab environment. Because this is a simulation and kind of a prototyping environment, sometimes it is possible to just it is possible that you might want to stick to the variables because you have loaded in big data and you don't want to wipe it out and load it again. It's possible here in Matlab. Now, of course, this is basic Matlab programming language features. We have ones, we have zeros, skip that. We have a cell structure, which is not really relevant, which is just a thing that sometimes might help out. And the basic usage for this is different data types. And in order to contain them in one container, you might want to use a cell. Because if you are trying to stack different sizes of data, you can see that it kind of messes up the data type here. Since I used a string here, it suddenly converted everything into a string array. So arrays by definition should be of the same type, because these are linear memories that should have a consistent type to it in order to work with them. Whereas cell is not really that, it preserves that. Let's just call this here. There we go. You can see that it is a cell array, and I can access the data in it, and it didn't change its data type. It is a special container, but it's not really that important for us, but you might want to know it. So let's actually create a script now. I will be using scripts most of the time, of course. And let's start with an if block. I'm just going to recap so that we, since we know programming probably, I'm just going to remind you of stuff and skip. Now, if you use double equal, it means that we are using a logic operator, the comparison operator. We want to compare if something is equal to something else. So here in this case, if there's something called I, we want to look if it's equal to 1. This returns actually true or false because it's a comparison. And based on that Boolean or logical value, if that's true, this block will run, line 4 will be executed, and it will be jumped. The remaining part will be jumped, and we will execute from line 8 on. So, for example, if we have I equals 1, by the way, there's a function called disp, which is printf sort of, but easier to use, more flexible. I can provide it I, it will show I. So I is equal to 1, and then I is not equal to 1. So that's it. So you can see, since I is equal to 1, it is equal to 1. If I run it again, by the way, I have to run it twice here. I is not equal to 1. Because of this Python integration thing, I have to run code twice. If you're using the Matlab GUI, you don't really have to execute it twice. So basically, if you know how to use if, you don't really have to use else. All that is happening if you're using that is basically this here. So if you have just one condition, then in case 1, this happens, otherwise this happens. So otherwise would be the not operation. So if it's equal to 1, this will be called. Otherwise, if I is not equal to 1, this will be called. So let's say we have just 2 values to compare. So in that case, it would look like this. We will have more cases, therefore, for example, let's have this here. So this is the 1-1 case, for example. Now, if you're using else, this would mean that we will have all the cases except this one here. So else would be then if this is not equal to 1, this is not equal to 1, but this one is equal to 1, or this one is not equal to 1, but this one is equal to 1, or Both are not equal to 1. So this would be else. So end. By the way, since we don't use any curly brackets like in C, we have just the statement if, and we end it with an end. It's kind of a Fortran-like approach, but it is what it is. Yeah, we don't use that much brackets in Matlab for some reason. So you can see that, yeah, we didn't display anything. Let's just display else. There we go. We're in the else case. So you have to keep in mind that if you have a condition and use else instead of this here, then just that one specific case is extracted from all the possible outcomes and all the other outcomes are living in else. But if you are using else if, like this, if you are using else if, you can just extract more possible combinations. For example, let's say this is not equal to 1. This is just another case. And you might be seeing where I'm going to, because all these possible outcomes can be distributed into else ifs, and then we can just skip one of them and then we will end up in else. So else if this here, instead of looking for this, you might just want to type in else, and that's it. So we can use if, else if, else if, else in order to take some actions based on different conditions. So this is basically if block, and it's there's nothing much to talk about it, but we can transition from the if block into something else, which would be, for example, this here. So let's say if I is equal to 1. And let's say I want to increase the value by 1. Before I do that, let's display the value of I. So that's it. There we go. We displayed 1 and we're basically done. So why did I code something like this? Well, basically, we have a starting point, I equals 1. Based on that starting point, we have a condition. I equals 1 is basically the condition. This holds. We display I, we increase I. If we would have been able to jump back to this if, then we could do some crazy stuff. Let's say, instead of being equal to 1, it should be less than or equal to 10. So let's run back again. Now you can see it starts with 1, increments it, it becomes 2. If I would have been able to jump back to if, it would satisfy this. 2 less than or equal to 10 would be a true statement. It would display I, it would increase I, and back again, until I is not equal to less than or equal to 10. I would repeat this, and then I would stop, basically. So if I want to jump back and repeatedly check on this condition and do based on the condition do stuff, then I use while. So while is essentially a copy paste of if. So I've copied and pasted quite some ifs. And if I run tests, you can see it goes up to 10, but once it reached 10 and basically even 11, the condition became false or invalid. It returns false at this point. So since it's false, it will jump to the end of all the ifs. Since they are identical, it will jump up to 79, line 79. So therefore, if you are copying and pasting if, it means that you are using a while loop. Since it doesn't really make sense to copy and paste if blocks, what we can do is we can just run it with a while loop. So this is basically converted behind the scenes into ifs, and it jumps back here, checks the condition, go through the operation, does it again, until it's breaking this condition and it goes on to its execution. So yeah, that's basically if and while. And yeah, we have also a for loop. Now, I didn't show you all the possible methods in creating arrays or vectors. Now, I have told you that you can use square brackets and then, for example, I equals 1, 2, 3. It is possible, but it's not the only way and also not the easiest way. What if I want to go on up to 100? I cannot type all the values. So what I can do is I can use a colon operator. It takes a starting point, an ending point, and it's basically it. And since we are using starting and ending points, and we didn't provide any increments, the increment is equal to 1. So therefore, if I run this and look what I is equal to, I can see that there are 100 columns. It is a row vector, and we have 100 entries. If I want to have a column vector, I can take the transpose, by the way, and run it. And you can see now they are displayed vertically. So therefore, by the way, it is also possible to use another column and define the increment. Let's define it like 0 up to 10. 0 and 10 by 10. There we go. So it starts from 0, increments 10, and reaches 100. So this is what we actually wanted to have. Now, based on this, what we can do is, or keep this in mind, and let me show you something. We can use a for loop. And in this for loop, what we can do is we can provide an array. And then maybe display I. So you can see actually that this is kind of a for each kind of looping. In some programming languages, there's something called for each. So it takes kind of lists or vectors and takes each element. For each element in that vector, it operates on it. So this is basically the Matlab version of for each. So if you provided a vector and then also a element variable, you can use that element variable and cycle through this vector here. And since the line 2 here generates also a vector, and since on the right-hand side we need a vector, what we can do is we can just convert this into the column notation, and it will not change anything. It will be still the same because, well, it's generating a vector. So let's test it. You can see it starts from 1, stops at 5, and the increment is 1. If you want to be specific about the increment, you can just give it with an additional column operator. So this is basically the C version here. Int I equals, it's like this. I equals 0, I less than or equal to 5, and then maybe I equals or plus equals to something like this. You get the idea. So this is basically the for loop. While loop, for loop, now we arrive at functions. Now, functions become important if you have a huge environment. You want to split up pieces of code that repeat stuff based on inputs and outputs, then you have to use functions. And the usage of functions is quite easy if you think about it like this. Let's assume a mathematical function here. Now, here, this is the usage of a sine function. You provided an input argument, maybe the angle, and you expect to have a return, namely the value that corresponds to the sine of 10, for example, in this case. Now, functions are also defined like this. Let's say we want to calculate the square of x. It is the same notation. We will have an input argument x, the output argument would be y. In short, it would look like this. So it should be looking like this, but I'm giving a trivial example in order to be able to, well, talk about the functions. So here, what we do is we just take the definition here, or the usage here, go here, create a script that has the same name, that shares the name, square.m. We give it the function keyword and paste it in and provide end. And that's basically it. So based on the usage, you can define your function. The only thing that you have to do is just take the name of the function, create a new file, a script file with the same name, and put in the definition or the usage as the definition, use the function keyword and you're good to go. The only thing that you have to do is, for this example, of course, is to assign this output variable in terms of the input variable to its value. Now, if we would use C, we would return Y. But here, since we can use it like y equals square x, it is also it is already implied that y is going to be returned. So this y equals here gets rid of the job of the return y statement that we usually use. And since we are getting the input, this is kind of a function block that has just one input, and then we have this square, and the input is x, the output is y. It takes the input, converts it into the output. So it's kind of self-explanatory, and that's the way we deal with functions here. If you want to return multiple things, you can do that in Matlab. You just have to, you just have to use a square bracket, and the reason for that is the following. Let's say the function something returns two outputs. Now, I can use an array here, let's say y and x, and it just returns something, doesn't even need anything. If you think about it, the values are stacked with the comma separator, and we have a square bracket. This means that this is an array. It is a 1x2 array, or a matrix, row matrix, which has two values in it. So it is possible to use this notation and come here and use this notation here. Func1, and in func1, let's say y is equal to 1, x is equal to 2. So here it is possible to call it, and as you can see, x and y are returned as expected. So multiple outputs can be returned in Matlab. The only issue would be to have different types of data, but it is also possible. So let's try that. Let's have AST and let's have an array. So you can see different data types can also be returned. The only thing is that it's not actually an array. It is a multi-output function, but it acts like an array and stacks them together and returns it. So Matlab has this unique way of returning multiple arguments, whereas this wouldn't be possible in C because you can just return x or y, not both of them. Of course, what you can do is you can just generate a struct in C and then give it x and y, and then return that struct maybe. That's a way of doing things. And as far as I know, in Matlab, it is somewhat similar to this, because the matrix structure is a unique data type in Matlab. So of course, you can also provide multiple inputs. It's just separated by comma as it is in the mathematics. So there's not that much difference to talk about. Yeah, what do we have? We have display. And it is also important to mention that sometimes in our code during the semester, we might want to combine text data with some data in order to display a nice message, in order to debug or to analyze stuff. For example, let's have k equals 2 for some reason, and let's display k and a message. For example, I want to display the coefficient is, and then I want to display that. So it is possible to display it like this, of course, but what if I want to generate a message that shows me k equals, so the coefficient k equals, and then the data of k. Now, of course, you cannot do this as far as I know. Let's see. Yeah, you have to combine it on your own. So if I want to add k to a string, I better convert it into a string, because if I want to add two objects together, I have to have the same size. So you can see the coefficient k equals 2, and you can even add another one, is obtained, for example. For some reason, we have this message here. You can see that I can convert numerical data into a string by using this string operator, because it's a constructor that takes in different data types and converts it into string. Sometimes it's also possible to deal with single quote characters, character arrays. And of course, I'm not going to use this, and also not char. I have to use num to str, which is a bit weird, I know, but yeah. Let me show you what happens if I put in char 10. As you can see, instead of converting the number 10 into a character array, it comes up with the ASCII value, as far as I know. Was it 97? Should be, yeah. The lowercase a is 97 in the ASCII table, and if you use the char function, it just converts it into the ASCII table value. Whereas I am interested in converting 97 into a string 97. So in the single quotes 97, that's what I'm after. In order to do that, I have to use this numerical to string function. Maybe the documentation can help us out here a little bit. Let's see. So it converts numeric array into a character array. So even though the name implies that it is a string, it returns single quote. So therefore, you can use num to str or string, single quote or double quote, in order to combine textual data and numerical data into just one textual data. So that's that. Sometimes we use this approach. Well, up to this point, I tried my best to recap the programming basics of Matlab. Now, in our course, we will use Matlab in 3 different ways. One of them is basic Matlab usage. The second one would be symbolic expression manipulation. Manipulations. And the third one would be the control system toolbox. Because we are dealing with control systems, we need to use control system specific functions that are already there. Therefore, I have covered the basic Matlab, but it is not really possible to recap everything at once. You have to get used to it, use it often in order to get used to it. Well, the symbolic expression manipulation part, I'm going to talk about that, and I'm going to also talk about the control system toolbox, the necessary functions. You are probably already familiar with the control systems toolbox. There are commands like step, there are root locus, body, and yeah, stuff like that. It goes on, like feedback, TF, etc. These are the functions that we might use PZMap. We will have transfer functions, so we can be interested in the step response of them. We can be interested in the root locus because of the feedback structure that we will use in order to tune the controller gain, or look for the look at the root locus and decide if we have a valid design or not, for example. We might be interested in the body plot, tells us much about the system. Feedback is used to just calculate the closed loop in a feedback. TF transfer function, define a transfer function, PZ map, poles and zeros map. So these will be used a lot, but our first step would be from the symbolic expression manipulation, because we will manipulate stuff, we will design, we will end up with a design, and with that design, we will look to verify if it's working, how well it is working. So therefore, we will use the control system toolbox. So this will be the last step. These two will be basically the first step in our weekly basis. So yeah. Up to this point, we have actually defined variables like x equals 2. But symbolic expressions and their manipulation is quite different. We want to have an unknown, a symbol, x, for example, and we want to be able to, for example, define the square of it, or we want to define a polynomial like x squared plus x plus 1, and we want to manipulate this to a certain point and then maybe solve a set of equations and end up with a value for x, and that x would be relevant in some case, and that is going to be the need here. So we need to define x on its own, but it is not really possible to do it with basic Matlab. There, for that matter, we can use actually the symbolic toolbox, and the symbolic toolbox allows us to define symbols like this. So I have defined the symbol x, but we have a problem, because by defining sim x, I expected that x can be used from now on, and I would be able to define x squared plus x plus 1 as an expression. But it still gave me the error unrecognized functional variable x. It doesn't know what x is, even though I have defined it. So you might be thinking that you have defined the symbol x, but as a Matlab user, if you are, you can see that it is stored in the answer variable, which is not basically x itself. So it is interesting to note that using sim_x does not really solve it. You have to assign it to x. So this is a bit interesting if you use it like this. So therefore, most of the time, I don't really use line 2. Instead of doing that, I just use this version here, where I define the symbols, multiple symbols maybe, and call it x. This way, you don't really have to reassign it to itself by using single quote x as a string, pass it to sim, and then store it in x. It's too much. You don't really have to do it. You can just get rid of it. You can just define it with one line and say, of course, from now on, if you see any x, that's going to be a symbolic expression. Now you can see I can define x squared plus x plus 1. And if I want to define an equation, for example, it's also possible. You can see x squared plus x plus 1 is equal to 0. So it's possible. Now, since I have this, let's call it equation 1. You can see I have now a variable called eq1. It is equal to this expression. Now, this is usually not possible in Matlab because it would not make sense. In Matlab, two equal signs would be a comparison, x would be undefined, and you would end up in an error message. But here, since x is a symbol, this means that it is a complex structured thing on the left-hand side that should be equal to 0. And the way that the sim engine, the engine behind the symbolic toolbox, works is that it has an unknown, it has a x squared operand, it has x, it has 1, and it knows that once you provide an x value to it, it will take the square, it will take itself, it will take 1 and combine them, sum them together in order to generate the value on the left-hand side. Once you have done that, you will end up with a value. But since this is an equation and we have two equal signs, this can also be used for other purposes like solve. You can solve this equation using the symbolic toolbox function solve. And now you have the solution to this equation here. So let's maybe make it like this. So we know the solution here. It's -1. And yeah, you can verify that it works. And you can also see that it has kind of an interesting way of displaying values here. In Matlab, if you have an operation, the result will be a floating point. But here you have symbolic expressions, which is quite powerful if you ask me. You can see that it's a complex number, but it comes from the second order equation solution. B squared minus 4ac is the discriminant, and then you have minus b, etc., etc. You get the idea. It is kind of following the solution rules. So it is doing the stuff that you would do for you. So it's not your usual calculation behind the scenes. It is kind of using the inverse method that we would use in order to solve this equation here. So therefore it is helping us, but keep in mind that this course is actually its exams and stuff is usually face-to-face. So therefore you should be able to solve it on your own with a pen and paper if it's not a high order or too difficult of a system to solve. Therefore, the symbolic toolbox just gets rid of the numerical solution part of our design process. Therefore, it is important to note that it is kind of following the rules that we also know for solutions for design. So we can solve this like this, or we can also define it like this. Since this is a polynomial now, this is a polynomial, we have also a function called roots. But before that, let me show coefs. So we have a function called coefs, which stands for coefficients. And in the control system toolbox, we are interested in coefficients, because if you remember, we have TF, and if I want to define a system, I provided the coefficients, 1 divided by s plus 1, for example. So therefore, I need to give it the coefficients in order to define the transfer function itself. So we are sometimes interested in the coefficients, and you can provide it the expression, and let's see what the result is going to be. 1 to 1. So yeah, this has coefficient 1, this is 2, and this is 1. It gave me the coefficients. So let me change the symbolic variable to s in order to be more consistent from now on. Let's say we have also something called k. So what would happen if I run this test script? What should be the result? Now, let's first try it. You can see that the result is not really what you might have expected. And the reason for that is that we have basically a tree structure. One of the unknowns is s squared, one of them is 2s, one of them is 1, and one of them is k. And the sim engine treats s and k as variables, as unknowns. Therefore, if you ask for the coefficients, you will get 1, 2, 1, and also 1. You might have expected that the outcome should be something like this, s squared 2s, 1 plus k, so therefore 1, 2, and 1 plus k. But that's not the case unless you provided the symbolic variable that it should keep track of. The coefficients in terms of s, then I would get what I want, hopefully. Let's see. Of course, it's kind of reversed here. We have k plus 1 first, lowest order, and then to the ascending order, but still better than the previous one. In order to get rid of the problem, you can provide an extra argument. But before that, let me show you something. What if we have s squared plus 1 plus k, and we are interested in the coefficient of that? Since it is, again, a tree structure, it has only 2 components in it. And the coefficients of those components are 1 and 1 plus k. Therefore, you get this instead of 1, 0, 1 plus k. So if you want to get the coefficients, all possible coefficients, since this is a polynomial, you should use all. And you can see that the order is also fixed. From now on, the highest order term will be on the left, the first element, and it will descend in order. So now I can immediately recognize that in terms of root table, in terms of control perspective, I can see that it is from ascending to descending order, and those are the coefficients of s squared and the constant term. So this is s squared plus k plus 1. I can immediately recover the polynomial by looking at this coefficient list. So therefore, if you are going to use the coef function, you'll use it like this: expression, variable, and in single quotation, all, because we want all the possible. Even if they are 0 and they are missing, they should be listed at 0 as 0. So if we don't have k, what we can do is we can take the coefficients and we can look for the roots of this. And you can see that if it's s squared plus 1, of course, the solution is plus minus I. And there you go. If this is a polynomial, these would be the roots of the polynomial. But let's have, for example, 3 here. You can see that it doesn't give me the numerical value that I might expect, because it gives me minus 3, the square root of that, times 1i. It's kind of a symbolic expression. If you would be in an exam, you would write exactly this here as a solution instead of the numerical value, probably. So, but it is still possible to do that, and it would be by using this double here. If it's a symbolic expression, because there's such a thing called symbolic expression, even though it has no unknowns in it, this is still an expression. You can convert it into a double in numerical value by using double. So let's run this. There we go. Now I can see that it is 1.73 something I, plus minus. So sometimes if you don't get the exact numerical values, you might want to use the conversion to double. Yeah, this is basically the usage of the symbolic toolbox. And there are some nice functions, some neat examples also, but we will see them alongside the problems that we will try to solve. Now, one of them is simplify, which is important. Let me talk about simplify. Yeah, let's have simplify. Let's have expression 1. Let's say this is s plus 1 divided by s plus 1. So the expression itself would look like this. And if we simplify it, it would look like this. Let's see. Well, it did also get rid of it. Interesting. But in some cases, this will not appear. It will not cancel each other out. And yeah, you already have seen it in the cosine squared plus sine squared example. If you don't simplify it, it will show you the same, but if you simplify it, it will get rid of it. And we will see examples where this becomes relevant. Of course, you get the idea from here, even though it didn't really simplify. Maybe I could try something like this. It still works. It still does it, even though we have defined it. But yeah, in some cases, it will not simplify because of reasons. And then we will try to force it to simplify. But sometimes also simplify will not help us out. And we'll see how to do that. There's also simplify fraction, etc. Now, let's look at 4 divided by 3, for example. It is 1.3333. But this is actually not correct. And sometimes Matlab lies to you for the sake of preventing problems. Now, if you call 3 times expression, you can see that it shows you 4. But based on this answer here, I would say that I should multiply this with 3, and it would be 3.9999. So this is for the sake of preventing problems, because this is actually not true. This has as many 3's as you can imagine behind the scenes. And if you multiply it by 4, Matlab remembers that this was, if you multiply it with 3, Matlab remembers that this was actually division by 3. So it takes it back and gives you the accurate number that it should be equal to. This is an approximation that you can see, but the actual value behind the scenes is different. And if you type it in manually, you can see it doesn't work. This is not the same as 3 times the expression, because the expression has much more detail in it. So in the symbolic toolbox, you can do something like this: 4 divided by 3. And as you can see, you can define it like that. And if you multiply this with 3, you'll see that it makes sense, because it is already 4 divided by 3, and you cannot type in manually the value of 4 divided by 3 symbolically. You're just giving the symbolical expression and multiply it with 3. 3 is converted into sim2, and then it is multiplied. So you don't really have to do it all the way like this, because it does it for you. So you can just use 3 instead of that. If one of the expressions is symbolic, everything is converted into symbolic. So that's important. So let's say we have that, but we want to convert it into double. It is possible, and I've shown it to you already. You can just do this, and you get the exact value here. And if you type it like that, let's see what happens. Still, Matlab keeps track of division by 3, because it's a big deal. So what would happen if I want to see, let's say, something like this: 4 divided by 3s. S. That can also work. Now I cannot convert into double. The problem is that I want to see 1.33s, because I want to see what it is approximately looking like. But it's not possible to convert it into a double, because s is not a variable that is compatible to convert into double, because s is an unknown. You cannot convert it. So let's see. There we go. We have a problem. And it says that it is not possible containing symbolic variables. I cannot convert it to a double array, apply something else, etc. So what should I do then? Well, we can change the way of displaying this stuff. And you can see now, if we use VPA directly, it will give you an approximate output with too many digits. If you want to limit the amount of digits, you can just provide the digits. You can say, I want to have 5 digits, and that's all. And it gives you this representation here. If we go to the documentation of VPA, variable precision arithmetic, arbitrary precision arithmetic, it's basically in order to give you a precision-based output. We will use it a lot because sometimes the expression become quite hard to estimate and to visualize. Then we would just go ahead and use VPA with comma digits, and it will show us the expression much more readable. That's that. Now we have again expand, collect, combine, factor, and stuff like that. But I'm going to show you the most important one, in my opinion. So this is actually a symbolic expression, not a transfer function at all. So let me state that this is a symbolic expression. we will define transfer functions as symbolic expressions, but you cannot apply step to it, you cannot apply root locus to it, body to it, nothing, because these require transfer function objects rather than symbolic expressions. So you can see it doesn't work because if we say help step, for example, the step function requires a system, a dynamic system, not a representation or a symbolic expression. So what can we do? Well, most of the time, we will need to convert this into a TF object. And TF objects, by definition, take the coefficients of the numerator and coefficients of the denominator. So in this case, I should provide 1 and 1, 4. This would be the same transfer function as this one here. So let's see. You can see that 1 divided by s plus 4 is the output of the symbolic expression, and 1 divided by s plus 4 continuous time transfer function, the result of line 5. You can apply step to the line 5 version, to the TF object. You can use any control system toolbox related function on this here, but not this one here. So therefore, we will first extract the numerator and denominator. So num then will be our function, and it will take a fraction, but it will return two outputs, one of them being the numerator, the other one being the denominator. As you can see, so it decomposed it into its numerator and denominator parts. Now we are still not there. We have to take the coefficients of the numerator, coefficients of the denominator, in order to be able to use this approach in line 5. So how can we do that? Well, we have seen that there's a function called coefs, the numerator in terms of s and all the coefficients in descending order. Same goes for then. So now we can see it kind of resembles the definition that I've given here. So let's call it num then. At this point, we still have, and I can show you that, we still have yeah, it gets rid of that, it makes it like that, but yeah, we still have an issue. Namely, these are still not numerical values. These are symbolic values. If there would be a result like 4 divided by 3, we would see it like a symbolic expression 4 divided by 3. So therefore, we have to convert them into double. And if you have an unknown in your expression, this will throw an error. But at that point, you shouldn't be able to convert that into a TF object, because if you have unknown parameters in it, it's not a TF object. So let's see. Test. What is the numerator? What is the denominator? You can even see that there are no square brackets. It's just an array. It is the Matlab version now. Now what I can do is I can define GS using these two variables, num and then. Now I have converted this into this. Now the nice thing here is that it will work for all the transfer functions that will be defined using this approach here. It will convert it into this one, and we will be able to call step on it. Let's see. There we go. Now, what is it good for? Before this course, probably what you did was you used root locus, or you used a pen and paper, designed a controller in the feedback. And then once you have obtained K, you've just plugged it in and defined the transfer function in line 7 and used line 8 in order to acquire the step response. But now what we can do is we can define a symbolic K, do some design steps, and once we are done, we can just get the controller coefficients that is calculated by Matlab, the symbolic toolbox, and then test it out. So now the pen and paper and the design process is also taking place in Matlab. Not only the verification step, which is like getting the step response, looking at the root locus or the pole zero map. Now we are also designing in Matlab. That's the way that will be the things that will be done in Matlab, and it will be throughout the course consistently used like this. Yeah, I have shown you num then that N and D is used here. So you can basically do this. I have shown you this part here. And if you are a lazy person like me, by the way, what you can do is you can just take this and create a function, call it sim to tf, for example, .m. And this function would be responsible of converting a symbolic expression into a transfer function object. And you can get rid of this. Of course, this will be provided. Of course, this is defined at return. There you go. What it does is it takes the expression, and we have a here we have a protocol or an assumption that all symbolic expressions depend only on S. This is my assumption. There should be nothing else than S. The only variable should be S. Then I would extract the numerator, denominator, look for all the S coefficients and convert them into double. If there's something like K or A or another unknown, this would crash. Once that's done, I have the vectors necessary provided to the TF object, UFGS, and return it back. So now what I can do is I can just skip this and skip this and use sim to TF, provide TSS, and I'll end up in a continuous transfer function. And change this. I can also change the order of it, 4 times S plus 1, something like that. And it converts it into the transfer function that is expected. It also works with the different numerator. You can see it works. So you can use sim to TF whenever it is necessary, because it's a basic thing. We might also need the inverse of this, where TF to sim, which we would call TF to sim, but we'll talk about it later. So yeah, these are the functions that we might use: TF, ZPK, SS, feedback. But once the time comes, we'll use them. So you can also check out the PDF here. I'm going to upload it. It will be available to you each week. So yeah, we have stuff that is written down here. And there's also a comprehensive example that shows you how to use these codes combined. Let me talk about this step portion here, this feedback portion here. So let's say we have that, we have defined GS. And for some reason, we have chosen K equals 1, and we have a feedback structure that looks like this. So basically like this. And like this. So let's assume we have a feedback structure like this, and our K value is equal to 1. So it's unit feedback, basically. We will be using this most of the time. So this is R, this is E, this will be U, and this will be Y. And there's a minus sign here, plus sign here, and that's basically our feedback structure. Now, if this is the case, you can use the feedback command and use kval times gs, and 1 is on the feedback loop. So this is feed forward, this is feedback. And then we would have ts. So this is nothing special, just ts is like this. And then we might want to look at step TS. And it creates this output here. Sometimes it might be necessary to extract the t and y vectors, namely the response and the time vector here. And in order to do that, we can just use y comma t, and you can see there are two output variables, two separate output variables. And you can see we have t and we have y. So we can also create a figure. Here CLF stands for clear figure, by the way. And there's hold on and grid on. I will be using them almost all the time. Hold on ensures that all the plot calls that will be made after this figure definition will be shown on top of each other. And grid on just places a grid for more readability or visual purposes. So you can just use t comma y and plot. The plot function uses the x-axis, the y-axis. You provide the x-axis, y-axis vectors, and it will create the 2D plot that you have already seen. So now you can see we have manually plotted it, but it is not easy to visualize it because the line width is not really that good. What I can do is I can adjust visual aspects of this plot here. You can see I've a more visible plot now. I can still increase it. Now you can see it is more readable. And you can use X label. There are some visual commands. I'm going to just show them to you. You can use single quotes, double quotes, whatever. Just call it time. Maybe YT. This will be the Y label, the X-axis label, the Y-axis label. You can give it a title, step response. These will come up quite often, so you will get used to it. So I've kind of now created my own step plot. And the nice thing about this is that I can, for example, look up the peak value here. So the max function here, if you provided a vector, it'll give you the maximum value. But if you use it like this, we get the index and the value. So let me change it. You can see that the value is 20, and the second element in this array is the maximum 1. So I can use this on Y and then plot the T index and Y index. But now the issue will be the following. We will not see the effect of this. So let's open it up. And there's no extra plot or no point on this peak point here. The reason behind that is that plot is a 2D plot. At least 2 elements should be provided to it for each axis, so it creates a plot, because it is trying to create a line. So if you have something like this, for example, this would be a line between 0, 1 and 1, 1. But if you don't provide 2 values for each axis, you're defining basically a point, but it is not possible to use a point and plot a line through that point, if it makes sense. So what you can do is you can provide it just a symbol, a marker, so that we get, hopefully, let's see, we should get X, but I'm not sure if we can see it. So let's increase the line width too. You can see now there's a point here, it's quite difficult to catch, but we can see that we have basically something on there. So let me increase the line width here a little bit more. Maybe give it a color black. So there we go. Of course, you can assign colors like this. It's a key value pair thing. You can just say color K for black, R for red, B for blue, G for green, etc. Let's have red. And you can also say marker, and the marker should be a square, for example, or X or dot, whatever you want. Now I've placed a square there, which is red. Or if you don't want to use it like this, if you want to have a short version, you give it a color and the marker. That should be the third argument. If that's the case, it'll just create the same here. So yeah, this might become handy for some reports and stuff, because we can export this. We can use print and then give it a name. Let's call it image1.png and then -dpng. Yeah, we can give it a resolution. We can also skip it. Now here it should appear in a second. There we go. We have an image. We have exported the figure as an image. So to automate stuff like that, I like to automate stuff like this. So maybe you can also use it. Maybe you want to do it. Well, I could look up the step info, the overshoot, the settling time, rise time, and I can also mark them on this plot. It is possible to do. The first 10% and 90% values are going to be necessary for that. You can do lots of stuff, customization on the plot. The step on its own, without any output argument, creates a plot, but it's not that much open to modification. So if you want to do it on your own, sometimes this would be the way of doing it. Well, yeah, I've talked about that. What else do we have? Well, this is about it for today, because yeah, we have this nice code. Let me just copy and paste it and talk about it. But this is already not really that difficult to do. Let me show it to you. So if I call close all, I'm closing all the figures. Clear just gets rid of all the previously defined variables, and CLC gets rid of the mess in the terminal. And if I run tests, I can just run tests. Now, it says property line width. Line width, because there's no space there. Sometimes copying and pasting might cause some issues, like here. Display name, because it has also an extra space here. There we go. Now, before I show the figure, let me explain you what the code really does. And at some point, you should be able to use Matlab in this way. So we have a symbolic part, which is not really necessary, but just to showcase. And we created a figure 1 here. Clear the figure. Hold on means, since I'm going to use the for loop here, they should appear on top of each other. Because if you don't hold on, all the previous plots will be cleared, will be wiped out, and you will see just the recent one. So grid on places a grid. This is the time vector. And we changed the variable a starting from 1 with increment 1 up to 5. And the fraction or the transfer function looks like a divided by s plus a. So it's basically a first order system with pole starting at 1, going up to 5 by increment 1. We take the numerator and denominator. You can use simply, you can use double coefs, comma s, comma all. We extract the numerator and denominator, convert them into vectors, convert that into a transfer function, which would mean actually that I can simplify it by using sim to tf. We don't really need that. And fraction. And that's basically it. So this should be g equals sim to tf at this point, because I have already coded this function. Why should I use extra steps? I get the step response, and I also assign it a name. This display name is actually for this legend here, in order to show and match the names with the plots. And then we have X label, Y label, title, and legend. That's it. So let's run it multiple times. And there we go. Now this is a custom plot that we created, and each color represents a certain pole. And for example, based on this data here, I can see that the blue one here is the pole 1. So if the pole is at 1, we have this dynamic here. If the pole is at 5, we have this dynamic here. And since we are incrementing the pole's magnitude, so it's at -1 and -5, as we increment the magnitude, we can see that in terms of speed of response, that if it increases, the speed of the response increases, or it takes less time to settle, or the settling time decreases. So these types of comments will be quite common in our weekly lectures, hopefully, because we are more interested in coding and examining stuff and understanding how systems really work, or how we can design controllers, or what we are actually doing behind the scenes, or the theoretical stuff, what it actually tries to tell us. Those types of things will be hopefully resulting in these types of plots and the codes that will try to help us out in understanding. So that actually concludes our today's lecture. Do you have any questions?